Now, in this lecture, we answer on two questions. In the first question, we find out the area of this trapezoid ABCD, and in the second question, we will find out the area of this green shape that is inside rectangle ABCD. So we start with the first question. So in the drawing, we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x, side DC equals to 7 over x. This is angle PAD, that is a right angle. This is angle ADC, that is also a right angle. Again, our mission is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Okay, so here, this is trapezoid ABCD. Here, side AB is parallel to the opposite side DC. The two parallel sides are defined as the bases, so AB is the first base, DC is the second base. So the bases must be parallel to each other. And what is the area of this trapezoid ABCD? The area of trapezoid ABCD equals to the sum of its two bases. In this case, the base is AB, the first base, and the second base is DC. But AB equals to B and DC equals to A. So the sum of the two bases is equals to A plus B times the height, that is h, over 2. Repeat again. The area of this trapezoid ABCD equals to the sum of its two bases, that is A plus B, times the height, that is h, over 2. Here, the height h must create 90 degrees with the two bases. You can see here that the height h creates 90 degrees with the base AB, and it creates also 90 degrees with the base DC. So in conclusion, we found out that the area of trapezoid ABCD equals to A plus B times h over 2. Okay. Again, the bases must be parallel to each other, and the height h must be perpendicular to the two bases. Okay. So, first of all, we will define the points of tangencies of trapezoid ABCD with this circle with letters. We define the point of tangency of tangent AB with this circle, this point, as E. Likewise, we define the point of tangency of tangent AD with this circle, this point, as F. We define the point of tangency of tangent BC with this circle, this point, as G. And finally, we define the point of tangency of tangent DC with this circle, this point, as H. So here we can implement rule 2 on this drawing. I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from common external point to a circle are equal. So in the drawing we have a circle, and this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule, all two are equal to each other. PA, this is to say PA equals to PB. So we can implement all two in our drawing. Why? Because in our drawing, if we focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle, tangent CAE and tangent AF. And according to rule 2, they are equal to each other. That is to say, AE equals to AF. So if we define the length of tangent AE as Y, then the length of tangent AF must be also equal to Y, because they are equal to each other according to rule 2. Likewise, we focus on this common external point, point B. From this common external point, point B, we have two tangents to this circle, tangent BE and tangent BG. And according to rule 2, they are equal to each other. That is to say, BE equals to BG. So if we define the length of tangent BE as Z, then the length of tangent BG must be also equal to Z according to rule 2. The next step we will focus on this common external point, point C. From this common external point, point C, we have two tangents to this circle, tangent CG and tangent CH. And according to rule 2, they are equal to each other. That is to say, CG equals to CH. So if we define the length of this tangent CG as M, then the length of this tangent CH must be also equal to M according to rule 2. And finally, we focus on this common external point, point D. From this common external point, point D, we have two tangents to this circle, tangent DH and tangent DF. And according to rule 2, they are equal to each other. This is to say, DH equals to DF. So if we define the length of tangent DF as T, then the length of tangent DH must be also equal to T according to rule 2. In the next step, we will define the length of this side AD of trapezoid ABCD as A. AD equals to A according to our definition. Likewise, we will define the length of tangent BC. We will define the length of this side BC of this trapezoid ABCD as B. So here BC equals to B according to our definition. So what is the value of side AB plus side DC? AB plus DC. AB, according to rule 2 in total, is equals to Y plus Z. Plus DC. DC equals to T plus M. So if we found out that AB plus DC equals to Y plus Z plus T plus M. What is the length of side AD plus side BC? here AD equals to y plus t plus BC. BC equals to z plus m. So if you found out that AD plus BC equals to y plus t plus z plus m. According to the algebraic identity that a plus b equals to b plus a, we can change the orders of the letters here. By changing the orders of the letters, we will not change the value of this expression. So here y plus t plus z plus m is equals to y plus z plus t plus m. Okay, so if I found out that AB plus DC equals to y plus z plus t plus m, and AD plus BC also equals to y plus z plus t plus m. So those two expressions, they are both equal to the same further expression, and therefore they are equal to each other. That is to say, AB plus DC equals to AD plus BC. This is equation 1. So AB, according to what is given as the equation, equals to x. So we substitute AB by x plus DC. DC, according to what is given as the equation, equals to 7 over x. So we substitute DC by 7 over x. And it is equals to AD plus BC. AD, according to our definition, AD equals to A plus BC. According to our definition, BC equals to B. So in conclusion, we found out that according to equation 1, x plus 7 over x equals to a plus b. So this is equation 1. In the next step, we will do a construction. This is to say, from point B, we will do perpendicular on DC. Again, from point B, we will do perpendicular on DC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and DC. This point is point S. So actually, by doing this construction, we created a quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. Therefore, this fourth missing element must be equal to 90 degrees in its size. Because of the fact that the sum of the three right angles is 270 degrees, so 270 degrees plus 90 degrees equals to 360 degrees. That is the sum of the angles in any quadrangle. So inside this quadrangle ABSD, we have four right angles. And according to rule 6, any quadrangle that has four right angles must be at least a rectangle, if not a square. So we will relate to this quadrangle ABSD that has four right angles as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle ABSD, side AB equals to the opposite side DS. But AB equals to X, according to what is given as the question. Therefore DS must be also equal to S. Likewise, according to the same rule, in the same rectangle ABSD, side AD must be equal to the opposite side BS. But side AD, according to our definition, equals to A. Therefore, BS must be also equal to A. Actually, by doing this construction, we created here the right triangle BSC. In this right triangle BSC, we already found out that side BS equals to A, the hypotenuse BC equals to B. So what is the length of this side SC? From the drawing, it is very easy to see that the length of this side SC is equals to DC minus DS. Again, SC equals to DC minus DS. So write it down. SC equals to DC minus DS. So SC equals to DC. DC is 7 over X according to what is given as the question, minus DS. We just write down found out that DS equals to X. So in total, SC equals to 7 over X minus X. Okay. SC equals to 7 over X minus X. So in the next step, I will copy this right triangle BSC in a new page, and we will implement the Pythagoras theorem on this right triangle BSC. Here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Again, side BS equals to A. The hypotenuse BC equals to B. And we just right now found out that the length of this side SC equals to 7 over X minus X. So actually, this is the right triangle side BSC is the copy from the original drawing. So according to the Pythagoras theorem, this right triangle BSC, BC square equals to BS square plus SC square. This is equation 2. BC equals to B, therefore BC square is B square, and it is equals to BS square. BS is A, therefore BS square is A square, plus SC square. SC is 7 over X minus X, therefore SC is 7 over X minus X square. So actually, if I know that according to equation 2, B square equals to A square plus 7 over X minus X square. So here we will use the algebraic identity that says that A minus B square equals to A plus B square plus minus 4 times A times B. According to this algebraic identity, the value of the expression 7 over X minus X square, if we just substitute 7 over X by A, if we just substitute 7 over X by A and X by B, we get that 7 over X minus X square will be equal to 7 over X plus X square minus 4 times 7 over X times X. Okay, so actually we can substitute 7 over X minus X square in this equation 2 by 7 over X plus X square minus 7 over X times X. We will do it now, and we will get that according to equation 2, B square equals to A square, and here 7 over X minus X square equals to 7 over X plus X square minus 4 times 7 over X minus 4 times 7 over X times X. Here we have X in the numerator and X in the denominator, so X will get cancelled, and we left only with minus 4 times 7, that is minus 28. So in conclusion, according to equation 2, we actually found out that B square equals to A square plus 7 over X plus X square minus 28. But according to equation 1, we have already found out that 7 over X plus X equals to A plus B. Okay, so we can substitute 7 over X plus X in this equation 2 by A plus B. We will do it now, and we get that according to equation 2, B square equals to A square plus, here we have 7 over x plus x squared. If 7 over x plus x squared, if 7 over x plus x equals to a plus b according to equation 1, it means that 7 over x plus x squared will be equal to a plus b squared. So we substitute 7 over x plus x squared by a plus b squared. And we have here minus 28. So according to equation 1, according to equation 2, actually found out that b squared equals to a squared plus a plus b squared minus 28. Here we will open the brackets in this expression, and we get that according to equation 2, b squared equals to a squared plus plus b squared. A plus b squared equals to a squared plus b squared plus 2 times a times b minus 28. So we found out that according to equation 2, b squared equals to a squared plus b squared plus 2 times ab minus 28. So here we have b squared on both sides of this equation too. So b squared we get cancelled. After I cancel b squared, in this side of the equation we left with nothing, that is to say 0. And it is equal to on the other side of the equation we have a squared plus a squared, that is 2a squared plus 2ab minus 28 equals to 0. So here we will add 28 to this equation 2, and we add according to this equation 2, here 0 plus 28 is 28. So 28 equals to 2a squared plus 2ab. So here we will divide this equation 2 by 2, and we get that according to equation 2, 28 over 2 is 14 equals to 2a squared over 2 is a squared plus 2ab over 2 is ab. So according to equation 2, we actually found out that a squared plus ab equals to 14. This is according to equation 2, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So we have here 2 equations. So what is the area of trapezoid ABCD? The area of trapezoid ABCD, according to the formula that I presented to you in the beginning of the lecture, the area is equal to the sum of its 2 bases times the height over 2. And we know that the 2 bases must be parallel to each other. So actually AB is parallel to DC. Why AB is parallel to DC? Because of the fact that we already found out that quadrilateral ABSD is a rectangle, and we also know that the opposite sides of a rectangle are parallel to each other. That is to say, rectangle ABSD, side AB is parallel to side DS. But DS is part of the straight line DC, and it's parallel to AB. So if part of the straight line is parallel to another straight line, then the straight line DC itself must be also parallel to the other straight line, that is AB. So conclusion, we actually found out that DC is parallel to AB, and therefore the two bases of trapezoid ABCD are DC and AB. And therefore the sum of the two bases equals to DC plus AB. And we have to multiply the sum of the two bases by the height. And we know that the height must create 90 degrees with the two bases. If side AD creates 90 degrees with the base AB, this again equals to 90 degrees. And side AD also creates 90 degrees with the base DC. Why? Because this again also equals to 90 degrees. And therefore AD is the height to the base. So times AD, that is the height, over 2. So in conclusion, we should found out that the area of trapezoid ABCD equals to DC plus AB, that is the sum of the two bases of trapezoid ABCD times the height, that is AD, over 2. And DC equals to x 7 over x, according to what is given as the question, plus AB. AB equals to x, also according to what is given as the question, times AD. AD equals to A, according to our definition, divided by 2. So here we have x plus 7 over x. But according to equation 1, x plus 7 over x equals to a plus b. So we can substitute x plus 7 over x in this expression by a plus b. We will do it now. So x plus 7 over x is a plus b. And we have to multiply it by a over 2. So in conclusion, we actually found out that the area of trapezoid ABCD equals to a plus b times a over 2. Here we'll open the brackets of this expression and we get that a times a is a square plus a times b is ab divided by 2. So the area of trapezoid ABCD equals to a square plus ab over 2. But we have already found out that a square plus ab equals to 14, according to equation 2. So we can substitute a square plus ab in this expression by 14. We will do it now. So in total this expression will be equal to 14 over 2, that is 7. In conclusion, I should found out that the area of trapezoid ABCD equals to 7 square units. And that is the answer to the question. I'll repeat again. The area of this trapezoid ABCD equals to 7 square units. So in the next step, I'll present to you the second question. Our mission in the second question is to find out the area of this green shape. So in the drawing we have a rectangle ABCD. We know that side CB of this rectangle ABCD equals to 7 units in its length. In addition, inside rectangle ABCD we have this is line segment CP that is equals to 4 units in its length. This is line segment PQ that is equals to 2 units. And finally, this is line segment AQ or QA that is equals to 5 units in its length. In addition, this is angle CPQ, that is a right angle, and this is angle PQA, that is also a right angle. I repeat again that our mission is to find out the area of this green shape. So first of all, we join point C and A together by a straight line. And we will define the intersection point of diagonal CA with line segment PQ, this point as M. Actually, when doing this construction, we created here those two angles. This is angle AMQ and this is angle PMC. Those two angles, they are defined as vertex angles, and vertex angles are equal to each other. So if we define the length and the size of this angle AMQ as theta, then the size of this angle PMC must be also equal to theta because of the fact that vertex angles are equal to each other. Okay, so it is given us the question that line segment PQ equals to 2 units in its length. So if we define the length of line segment PM, this is line segment PM. So if we define the length of this line segment PM as X, then the length of this line segment MQ must be equal to PQ minus PM. So I'm writing down MQ equals to PQ minus PM. So MQ equals to PQ, PQ is 2, minus PM, PM is X according to our definition. So in total, MQ equals to 2 minus X. MQ equals to 2 minus X. In the next step, we'll focus on this right y triangle AMQ. In this right y triangle AMQ, this angle equals to theta, this angle equals to 90 degrees, therefore the missing third angle, this angle must be equal to 90 degrees minus theta. Why? Because of the fact that 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, according to the same logic, we'll focus on this right green small triangle PCM. In this right small triangle PCM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we prove that those two right triangles are similar to each other. So I write it down. We prove that the right triangle AMQ is similar to this right small green triangle PMC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. So this is angle AMQ. In the right triangle AMQ, and it is equal to this angle, it is actually angle PMC. In the right green small triangle PMC. Repeat again, angle AMQ in the right triangle AMQ equals to angle PMC in the right triangle PMC. They are both equal to theta, therefore they are equal to each other. In addition, those two angles, they are both right angles, therefore they are equal to each other. Actually, this is angle AQM. In the right triangle AMQ, right triangle AMQ, and it is equal to this angle. It's actually angle CPM. In the right green small triangle PMC. So repeat again, angle AQM in the right triangle AMQ equals to angle CPM in the right triangle PMC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So actually this is angle MAQ in the right triangle AMQ, and it is equal to this angle, this is actually angle PCM in the right triangle PMC. Repeat again, angle MAQ in the right triangle AMQ equals to angle PCM in the right triangle PMC. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the right triangle AMQ are correspondingly equal to all the three angles in the right green small triangle PMC. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right triangle AMQ is similar. This is the sign of similar to the right green small triangle PMC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PM in the right triangle PMC over side MQ in the right triangle AMQ is equals to side PC in the right triangle PMC over side AC in the right triangle AMQ. And again, we derive that PM over MQ equals to PC over AQ. PC over AQ. Repeat again. We derive that PM over MQ equals to PC over AQ. So PM equals to x, according to our definition, over mq. We already found out that mq equals to 2 minus x, and it is equals to PC. PC is 4 over AQ. AQ is 5 according to what is given as the question. So in conclusion, we found out that x over 2 minus x is equals to 4 over 5. Here we cross multiply this equation, and you get that 5x equals to 4 times 2 minus x. So here we will open the brackets on this side of the equation, and we get that 5x equals to 4 times 2 is 8, minus 4 times minus x is minus 4x. So here we add 4x to this equation, and we get that 5x plus 4x is 9x. So 9x equals to 8. So here we divide this equation by 9, and finally we get that x equals to 8 over 9, or x equals to 8 ninths. So x equals to 8 ninths. Yeah. This is 9:07 p.m. That's equal to x, and x equals to 8 ninths. It equals to 8 ninths. So what is the length of MQ? MQ is 2 minus x. 2 is 18 ninths. Again, 2 is 18 ninths. And therefore 2 minus x equals to 18 ninths minus x, that is 8 ninths. So 18 ninths minus 8 ninths is 10 ninths. Therefore, in total 2 minus x equals to 10 ninths. Okay, so if we're going to find out that the length of 9:07 p.m. that is equal to x equals to 8 ninths, and the length of this 9:07 MQ that is equals to 2 minus x equals to 10 ninths. In the next step, I will copy the line AQPC, this line AQPC. In your page, we will analyze this line AQPC. Side AQ equals to 5 units in itself, according to what is given as the question. And angle AQP equals to 90 degrees. Line segment PQ equals to 2 units in its length. And this angle QPC equals to 90 degrees, it is a right angle. And finally, line segment CP or PC equals to 4 units. So actually, this is line AQPC that I copied from the original drawing. In the next step, we'll extend the straight line AQ by straight line. When you extend a straight line by straight line, the result must be a straight line. Therefore, this is a straight line. Okay. So if you focus on the upper side of this straight line at point Q, here the sum of the angles must be equal to 180 degrees, according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of this straight line at point Q must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of this straight line at point Q? We have this angle that is equals to 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. And in order to complete the sum of the angles on the upper side of this straight line at point Q to 180 degrees, the missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction, that is to say, from point C, we will draw perpendicular on the extended AQ. Again, from point C, we will draw perpendicular on the extended AQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular for point C and the extended AQ, this point as N. By doing this construction, we created a quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the fourth missing angle must be equal to 90 degrees in its size. As I already explained before, that here the sum of the three angles is 270 degrees plus the 90 degrees equals to 360 degrees. That is the sum of the angles in any quadrilateral. So inside quadrilateral PC and Q, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be a rectangle, not a square. So we relate to this quadrilateral PC and Q as a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PC and Q, side PQ must be equal to the opposite side CN, but PQ equals to 2, therefore CN must be also equal to 2. Likewise, according to the same rule, in the same rectangle PC and Q, side PC must be equal to the opposite side QN, but PC is 4, therefore QN must be also equal to 4. In the next step, we will join point C and A together by a straight line. By joining points A and C, by joining points A and C, we created the right triangle ACN. In the next step, we implement the Pythagoras theorem on this right triangle ACN. According to the Pythagoras theorem, in the right triangle ACN, AC square equals to Cn square plus An square. But again, AC square equals to Cn square plus An square. Now I take ACN. So AC square, that is the square of the hypotenuse, equals to Cn square. Cn is 2, therefore Cn square is 2 square, that is 4, plus An square. An in total equals to 5 plus 4, that is 9. An equals to 9, therefore An square is 9 square, that is 81. So in total we found out that AC square equals to 4 plus 81, that is 85. So AC square, that is the square of the hypotenuse of the right triangle ACN, equals to 85. It has given us the question that ABCD is a rectangle. And we also know that all the angles in any rectangle, all the angles inside any rectangle are right angles. And especially this is angle ABC, that is a right angle. It is equals to 90 degrees in its size. So it's true in any rectangle. So in the next step, I'll copy this right big triangle ABC in a new page, and we will implement the Pythagoras theorem on this right triangle ABC. Side CB equals to 7 units in its length, and we just write down found out that the square of the product AC, that is to say AC squared, equals to 85. Here, AC squared equals to 85. Here by PT is abbreviation for Pythagoras theorem. Actually, this is the right angle ABC that I copied from the original drawing. In this right angle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus CB squared. We have already found out that AC squared is 85, therefore we substitute AC squared by 85. So 85 equals to AB squared. AB is the missing side, so we leave it as it is. So it is AB squared plus CB squared. We know that CB is 7, therefore CB squared is 7 squared, that is 49. So in conclusion, we have found out that 85 equals to AB squared plus 49. Here we subtract 49 from this equation, and we get that AB squared equals to 85 times 49 is 36. So AB squared equals to 36. Here we'll take a root out of this equation, and we get that AB equals to the square root of 36, that is 6. So AB equals to 6 units in its length. Here, this is side AB, that equals to 6 units in its length. Our mission is to find out the area of this green shape. So, what is the area of the green shape? The area of the green shape equals to the area of the big right triangle ABC. But because of the fact that the area of the big right triangle ABC includes the area of this white right triangle AMQ, we have to subtract from the area of this big right triangle ABC the area of the white right triangle AMQ, because we are interested only on the green area. So we subtract the area of this right triangle triangle AMQ from the area of triangle ABC. So it is minus the area of the white triangle AMQ. And because of the fact that the green small right triangle PCM is not included in the area of the right big triangle ABC, we have to add to the area of the big triangle ABC the area of this right triangle PMC that is not included in the area of triangle ABC. So it is plus the area of this small right triangle PMC. So repeat again, the area of the green shape in total equals to the area of the green right triangle ABC minus the area of the white right triangle AMQ plus the area of the right small green triangle PMC. So what is the area of the right triangle ABC? The area of the right big triangle ABC equals to the base, that is AB, times the height to the base, that is CB, over 2. So in total, the area of triangle ABC equals to AB times CB over 2, minus the area of the right triangle AMQ. What is the area of the right triangle AMQ? Is equals to the base, that is AQ, times the height to the base, that is MQ, over 2. Repeat again. We found out that the area of the right triangle AMQ equals to AQ times AQ times MQ over 2. And we have to add the area of the right small green triangle PMC. The area of the right small green triangle PMC equals to the base of the triangle, that is PC, times the height to the base, that is PM, over 2. Repeat again, the area of the right small green triangle PMC equals to PC times PM over 2. So AB equals to 6 times CB is 7 divided by 2. So in total, the area of the big right triangle ABC equals to 6 times 7 over 2, minus the area of triangle right triangle AMQ. It is equals to AQ, that is 5, times MQ. MQ is 10 nines, over 2. So in total, the area of the right triangle AMQ equals to 5 times 10 over 2 times 9. Plus the area of the right green small triangle PMC is equals to PC. PC is 4 times PM. PM is 8 nines divided by 2. So in total, we found out that the area of the right small green triangle PMC equals to 4 times 8 over 2 times 9. So here we have the area of triangle ABC equals to 6 times 7 over 2. 6 times 7 is 42, and 42 over 2 is 21. And this expression equals to the area of the right triangle AMQ. Here we have 10 over 2 is 5, and 5 times 5 is 25. So in total, this expression equals to minus 25 over 9. So 25 over 9 is actually the area of the right triangle AMQ, plus the area of the right green small triangle PMC, that is equals to 4 times 8 over 2 times 9. Here 10 over 2 is 4, and 4 times 4 is 16. So in total, this expression equals to 16 over 9. So in total, we found out that the area of the green shape equals to 21, that is the area of the big right triangle ABC. Here we have minus 25 over 9 plus 16 over 9. So here we have 21, and minus 25 plus 16 is minus 9. So in total, this expression equals to minus 9 over 9. So the area of the green shape equals to 21, and minus 9 over 9 is minus 1, and 21 minus 1 is 20. So if we found out that the area of the green shape equals to 20 square units. Okay, the area of the green shape in total equals to 20 square units. Repeat again, the area of this green shape that is inside rectangle ABCD is equals to 20 square units. So in the next step, I will summarize the lecture. We start with the first question, of course. Our mission in the first question is to find out the area of this trapezoid ABCD. So in the drawing we have a circle that is inscribed by this trapezoid ABCD. In addition, we know that side AB of trapezoid ABCD equals to x units in its length, and this is side DC that equals to 7 over x units in its length. This is angle BAD that is a right angle, and this is angle ADC that is also a right angle. I repeat again that our mission is to find out the area of this trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. Repeat again. A trapezoid is a quadrilateral with one pair of parallel sides. Here we have quadrilateral ABCD, and because of the fact that side AB is parallel to side DC, this quadrilateral ABCD is defined as a trapezoid. And the parallel sides are defined as the bases of this trapezoid. So AB is the first base and DC is the second base. So, what is the area of trapezoid ABCD? The area of trapezoid ABCD equals to the sum of its two bases. It is AB plus DC. But AB, according to our definition, is B and DC is A. Therefore, AB plus DC actually equals to A plus B times the I to the base, that is H over 2. So the area of this trapezoid ABCD equals to A plus B times H over 2. The height H must create 90 degrees with the two other bases. And indeed, here H creates 90 degrees with the base AB, this angle equals to 90 degrees. And it creates also 90 degrees with the base DC, because this angle equals to 90 degrees and this angle also equals to 90 degrees. So in conclusion, the area of trapezoid ABCD equals to A plus B times H over 2. A plus B on the two bases times the height that is H over 2. Again, the height H must create 90 degrees with the two bases. So, first of all, define the point of tendencies of trapezoid ABCD with this circle with letters. We define the point of tendency of tangent AB with this circle, this point as C. We define the point of tendency of tangent AD with this circle, this point as F. We define the point of tendency of tangent BC, this point of tangent BC with this circle, this point as G. And finally, we define the point of tendency of tangent DC with this circle, this point as H. So now we can implement here in this domain rule 2. So according to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the domain we have a circle, this is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. According to all two, they are equal to each other. That is to say PA equals to PB. We can actually implement this all two in our domain. In our domain, if you focus on this common external point, point A, from this common external point, point A, we have two tangents to this circle, tangent AE and tangent AF. And according to all two, they are equal to each other. That is to say AE equals to AF. So if we define the length of this tangent AE is y, then the length of tangent AF must be also equal to y. Likewise, if you focus on this common external point, point B, from this common external point, point B, we have two tangents to this circle, tangent BE and tangent BG. And according to all two, they are equal to each other. That is to say BE equals to BG. So if we define the length of tangent BE is Z, then the length of this tangent BG must be also equal to Z. Likewise, we focus on this common external point, point C. From this common external point, point C, we have two tangents to this circle, tangent CH. Again, from this common external point, point C, we have two tangents to this circle, tangent CH and tangent CG. And according to all two, they are equal to each other. That is to say, CG equals to CH. So if we define the length of tangent CG as M, then the length of tangent CH must be also equal to M according to all two. And finally, we focus on this common external point, point D. From this common external point, point D, we have two tangents to this circle, tangent DF and tangent DH. And according to all two, they are equal to each other. That is to say, DF equals to DH. So DF equals to DH. So if we define the length of tangent DF as T, then the length of tangent DH must be also equal to T according to all two. Okay, so in the next step, we define the length of this side AD as A, and we define the length of this side BC of trapezoid ABCD as B. So what is the value of AB plus DC? AB is Y plus Z, and DC is T plus M. So in total, AB plus DC equals to Y plus Z plus T plus M. Likewise, we added side AD to side BC. So what is the value of AD plus BC? AD is Y plus T, and BC is Z plus M. So in total AD plus BC, AD plus BC, AD plus BC equals to Y plus T plus Z plus M. So here we can change the order of the letters here according to the algebraic identity that A plus B equals to B plus A. So instead of Y plus T plus Z plus M, we can write down Y plus Z plus T plus M. We just change the orders and it is another. So according to I actually found out that AB plus DC equals to Y plus Z plus T, Y plus Z plus T plus M, and AD plus BC also equals to Y plus Z plus T plus M. So those two expressions in the green color are equal to the same first expression, and therefore they must be equal to each other. That is to say, AB plus DC must be equal to AD plus BC. AB is X, DC is 7 over X, AD is A, and BC is B. So in total we found out that according to equation 1, X plus 7 over X equals to A plus B. In the next step, we did a construction, that is to say, from point B we draw perpendicular on DC. Again, from point B we draw perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and DC. This point is point S. Actually, by doing this construction, we created a quadrilateral ABSD. Inside this quadrilateral ABSD, we have 1, two free right angles. The sum of free right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle in total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Why? Because 270 degrees, that is the sum of the two other three angles, plus 90 degrees is 360 degrees, that is the sum of the angles in any quadrilateral. So inside quadrilateral A, B, S, D, we have 4 right angles, and according to rule 6, any quadrilateral that has four right angles must be, it is a rectangle if not a square, so we relate to this quadrilateral A, B, S, D that has 4 right angles as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABSD, side AB must be equal to side DS. But AB is x, therefore DS must be also equal to x. Likewise, according to the sum rule in the sum rectangle, so in rectangle ABSD, side AD must be equal to the opposite side BS. But AD is A, therefore BS must be also equal to A. By doing this construction, we get the idea of the right angle BSC. In the right angle BSC, side BS equals to A, the hypotenuse BC equals to B. So what is the length of this side SC? From the drawing it is very easy to see that SC equals to DC minus DS. Again, SC equals to DC minus DS. DC is 7 over x and ds is x. So in total, SC equals to 7 over x minus x. Yeah, SC equals to 7 over x minus x. In the next step, I'll go with this right triangle BSC in Olympiad and we implemented the Pythagoras theorem on this right triangle BSC. Quickly, this is the right triangle BSC that I copied from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle BSC is BC, and therefore the square of the hypotenuse is BC square, and it must be equal to BS square plus SC square. Repeat again, according to this equation 2, BC square equals to BS square plus SC square. BC is B, therefore BC square is B square, and it equals to BS square. BS is A, therefore BS square is A square, plus SC square. SC is 7 over x minus x, therefore SC square is 7 over x minus x square. So we actually found out that according to equation 2, b square equals to a square plus 7 over x minus x square. Here we used the algebraic identity that says that a minus b square equals to a plus b square minus 4 times ab. So according to this algebraic identity, if we just substitute 7 over x by a and x by b, we get that the value of this expression 7 over x minus x squared will be equal to 7 over x plus x squared minus 4 times 7 over x times x. Okay, therefore we can substitute 7 over x minus x squared in this equation 2 by 7 over x plus x squared minus 4 times 7 over x times x. We did it. And we should found out that according to equation 2, b square equals to a square, and 7 over x minus x square equals to 7 over x plus x square. And here we have x in the numerator and x in the denominator, so x will get cancelled. So in total we have in this expression equals to minus 4 times 7, that is minus 28. So if we're going to actually found out that b square equals to a square plus 7 over x plus 7 over x plus x squared minus 28. This is according to equation 2. Well, according to equation 1, we already found out that 7 over x plus x equals to a plus b. Therefore, we can substitute 7 over x plus x squared in this equation. We can substitute 7 over x plus x in this equation 2 by a plus b. We did it and actually found out that according to equation 2, b squared equals to a squared, and here if 7 over x plus x equals to a plus b, it means that 7 over x plus x squared must be equal to a plus b squared. So in total, we found out that according to equation 2, b squared equals to a squared plus a plus b squared minus 28. Here we open the brackets of this expression, and finally found out that according to equation 2, b squared equals to a squared, and a plus b squared equals to a squared plus b squared plus 2 times ab, and we have here also minus 28 as a quote from equation 2. So here we have b squared on both sides of the equation, so b squared will get cancelled. So in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have a squared plus a squared, that is 2a squared, plus 2ab minus 28. Here we added 28 to this equation 2, and finally found out that 0 plus 28 is 28. That is equals to 2a squared plus 2ab, and 28 minus 28 is 0. So in total, according to equation 2, we found out that 28 equals to 2a squared plus 2ab. We divided this equation 2 by 2, and finally found out that 28 over 2 is 14, and it is equals to 2a squared over 2 is a squared, and plus 2ab over 2 is ab. So according to equation 2, we found out that 14 equals to a squared plus ab, while according to equation 1, we have already found out that x plus 7 over x equals to a plus b. So we have those two equations. Now we can find out the area of trapezoid ABCD. According to the formula that I presented to you at the beginning of the lecture, the area of this trapezoid ABCD must be equal to the sum of its two bases times the height over 2. The two bases must be parallel to each other. Here, actually side AB is parallel to side DC. Why side AB is parallel to side DC? Because of the fact that ABSD is a rectangle, and you know that the opposite sides of a rectangle are parallel to each other. So in rectangle ABSD, side AB is parallel to the opposite side DS. Okay, AB is parallel to DS. But DS is part of the straight line DC, and it's parallel to AB. So if part of the straight line is parallel to another straight line, then the straight line itself, the straight line DC itself, must be also parallel to the other straight line, that is AB. So if we found out that DC is parallel to AB, and therefore the two bases, the two parallel sides in trapezoid ABCD are DC and AB, and therefore DC and AB are the bases of this trapezoid ABCD, and therefore the sum of the two bases is AB plus DC, or DC plus AB. Again, the sum of the two bases of trapezoid ABCD equals to DC plus AB, because DC is parallel to AB, times the height over 2. The height as creates 90 degrees with the two bases, and indeed side AD creates 90 degrees with the base AB, and it creates 90 degrees with the base DC. Therefore, AD is the height. So in total, we found out that the area of trapezoid ABCD equals to DC plus AB, that is the sum of the two bases, times the height, that is AD over 2. DC is 7 over x, and AB is x. AD is A according to our definition, divided by 2. So in conclusion, we found out that the area of trapezoid ABCD equals to 7 over x times x, 7 over x plus x times a over 2. But we already found out that 7 over x plus x equals to a plus b, so we can substitute 7 over x plus x by a plus b. We did it. Here 7 over x plus x is a plus b, and we have to multiply it by a over 2. Here we open the brackets of this expression, and found out that a times a is a squared plus ab divided by 2. So if we found out that the area of trapezoid ABCD equals to a squared plus ab over 2. But according to equation 2, a squared plus ab equals to 14. So we can substitute a squared plus ab by 14. We did it. So a squared plus ab is 14. So in total this expression equals to 14 over 2, that is 7. So in conclusion, we found out that the area of trapezoid ABCD equals to 7 square units. So again, the area of this trapezoid ABCD equals to 7 square units. We finished with the first question. In the next step, I actually presented to you how to find out the area of the green shape in the second question. Repeat again, our mission in the second question was to find out the area of this green shape. So, in the drawing we have rectangle ABCD. We know that side CB of this rectangle ABCD equals to 7 inches length. In addition, inside this rectangle ABCD, this is side CP that is equals to 4 inches length. This is side PQ that is equals to 2 inches length. This is again CPQ that is right angle. This is 9 segment QA that is equals to 5 units in its length. This is angle PQA that is right angle. Again, our mission is to find out the area of this green shape. So in the first step, we joined point C and A together by straight line. So we defined the intersection point of diagonal CA with line segment PQ, this point as M. By doing this construction, we added here vertex angles. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if angle CMP equals to theta, then angle QMA must be also equal to theta, because both of them are vertex angles, and vertex angles are equal to each other. In the next step, we focus on this right angle AQM. In this right angle AQM, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, according to the same logic, if we focus on this right small green triangle PMC, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. In the next step, we proved that those two right triangles are similar to each other. That is to say, we proved that the right triangle AQM is similar to the right small green triangle PCM. So why those two right triangles are similar to each other? First of all, those two angles are both equal to theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on theta, therefore they are equal to each other. So we should prove that all the three angles in the right triangle AQM are correspondingly equal to all the three angles in this right small green triangle PMC. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. That side PM in the right triangle PCM over side QM in the right triangle AMQ is equals to side PC in the right small green triangle PCM over side AQ in the right triangle AQM. I repeat again, we will derive that PM over MQ equals to PC over AQ. PM is X, MQ is 2 minus X, PC is 4, and AQ is 5. So in conclusion, we found out that X over 2 minus X equals to 4 over 5. Here we cross multiply this equation, and finally found out that 5x equals to 4 times 2 minus x. Here we open the brackets on this side of the equation, and found out that 5x equals to 4 times 2 is 8, and 4 times minus x is minus 4x. So in conclusion, we found out that 5x equals to 8 minus 4x. Here we added 4x to this equation, and finally found out that 5x plus 4x is 9x, so 9x equals to 8. Here we divided this equation by by 9, and finally found out that x equals to 8 over 9, or x equals to 8 ninths. So this is now 7 p.m. That is equal to x according to our definition. So x equals to 8 ninths. So what is the length of MQ? MQ is 2 minus x. 2 is 18 ninths, and therefore 2 minus x is 18 ninths minus x, and x is 8 ninths. So in total, 2 minus x equals to 18 ninths minus 8 ninths. 18 ninths minus 8 ninths equals to 10 ninths. So in total, we found out that MQ that equals to 2 minus x equals to 10 ninths, and PM that equals to x equals to 8 ninths. In the next step, I copy this line AQPC in a new page and analyze this line AQPC. Actually, this is line AQPC, the default of the original drawing. Line segment AQ equals to 5, line segment PQ equals to 2, line segment PC equals to 4. This angle QPC is a right angle, and this is angle AQP that is also a right angle. So in the next step, we extended the straight line AQ by straight line. When you extend the straight line by straight line, the result is a straight line. So this is the straight line. So if you focus on the upper side of this straight line is point Q, here the sum of the angles must be equal to 180 degrees. According to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of this straight line is point Q? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we did the construction. That is to say, from point C, we do perpendicular on the extended AQ. Again, from point C, we do perpendicular on the extended AQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and the extended AQ, this point, as N. By doing this construction, we created a quadrilateral PC and Q. Inside this quadrilateral PC and Q, we have 1, 2, 3 angles. 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral PC and Q, we have 4 right angles. And according to rule 6, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will to this quadrilateral PC and Q as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle PC and Q, side PQ must be equal to the opposite side CN. But PQ is 2, therefore CN must be also equal to 2. Likewise, according to the same rule, in the same rectangle PC and Q, side PC must be equal to the opposite side QN. But PC is 4, therefore QN must be also equal to 4. In the next step, we join points A and C together by straight line. By joining points A and C, we get the right triangle ACN. So in the next step, we implemented the Pythagoras theorem on this right triangle PCN, ACN. According to the Pythagoras theorem, in this right triangle ACN, AC square equals to CN square plus AN square. Again, AC square equals to CN square plus AN square. So AC square equals to CN square. CN is 2, therefore CN square is 2 square, that is 4, plus AN square. AN in total equals to 5 plus 4, that is 9. Therefore AN square is 9 square, that is 81. So we found out that AC square equals to 4 plus 81, that is 85. So AC square, that is the square of the hypotenuse of this right triangle, equals to 85. So actually given us the question that ABCD is a rectangle, and you know that all the angles inside any rectangle are right angles. And especially this angle ABC is a right angle. So I copied this green big, this big right triangle ABC in a new page, and we implemented the Pythagoras theorem on this right big triangle ABC. This is the right big triangle ABC that I call it on the original drawing. It is given us the equation that side CB equals to 7 in its length, and we just write our found out that AC square equals to 85. So according to the Pythagoras theorem, this right triangle ABC, AC square equals to AB square plus BC square. AC square is 85, therefore we substitute AC square by 85, and it equals to AB square. AB square is the missing side, so we leave it as it is, plus CB square. CB is 7, therefore CB square is 7 squared, that is 49. So in conclusion, we actually found out that 85 plus AB square plus 49. Here we subtracted 49 from this equation, and finally found out that AB square equals to 85 minus 49 is 36. So AB square equals to 36. We took the root of this equation, and finally found out that AB equals to the square root of 36, that is 6. Here, this is side AB, this equals to 6 units in itself, and this is side CB, this equals to 7 units in itself. So what is the area of the green shape? The area of the green shape must be equal to the area of the right big triangle ABC, and because of the fact that the area of the right triangle ABC includes this white triangle, we have to subtract from the area of triangle ABC the area of this white triangle, and we have to add to the area of triangle ABC the area of this right small green triangle PCM that is not included in the area of triangle ABC. So in conclusion, we found out that the area of the green shape equals to the area of the big right triangle ABC minus the area of this white right triangle AQM plus the area of the right green small triangle PCM. And again, the area of the green shape in total equals to the area of the right big triangle ABC minus the area of the right triangle AMQ minus the area of the green small right triangle PMC. The area of the right big triangle ABC equals to the base that is AB times the height to the base that is BC over 2 minus the area of the green right triangle AMQ. The area of the green right triangle AMQ equals to the base that is AQ times the height to the base that is QM over 2. Because again, the area of the right triangle AMQ equals to the base AQ times the height to the base that is AMQ over 2 plus the area of this green right triangle green right small triangle PMC. The area of the green small right triangle PMC equals to the base that is PC times the height to the base that is PM over 2. Repeat again, the area of the green small right triangle PMC equals to the base that is PC times the height to the base that is PM over 2. So the area of the green shape equals to AB6 CB7 over 2. So in total, the area of the green right triangle, the area of the triangle, the big triangle ABC equals to 6 times 7 over 2, minus the area of the right triangle AMQ. AQ is 5, MQ is 10 over 9 divided by 2, plus the area of the green small triangle PMC. This equals to PC. PC is 4 times PM is 8 ninths divided by 2. So in conclusion, we found out that the area of the green shape equals to 6 times 7 over 2, that is 21, minus 5 times 10 over 2 times 9, that is minus 25 over 9, and 4 times 8 over 2 times 9 equals to 16 over 9. So the area of the green shape in total equals to 21, and here we have minus 25 plus 16 over 9. Minus 25 plus 16 is minus 9, so this expression in total equals to minus 9 over 9. Minus 9 over 9, so the area of the green shape in total equals to 21 minus 9 over 9. Minus 9 over 9 is minus 1. So in total, the area of the green shape equals to 21 minus 1, that is 20. So if we found out that the area of the green shape, the area of the green shape equals to 20 square units, because again the area of this green shape equals to 20 square units. Okay, thank you very much.